Hey everyone, so welcome to our final video of the series. In the last video we implemented the alpha-beta-pruning algorithm and built a really nice AI as our opponent. But our AI at the moment searches the tree for a fixed depth value of 5 currently. So as I told you before, in this video we are going to implement the iterative deepening algorithm or method, whichever you call that, so that this player can search deeper trees in each iteration as long as it has additional time. So and before I start this video, I want to point out something. So I've been sharing the GitHub repository link of the program, so of this code, in the descriptions of each video. So feel free to contribute open issues, open merge requests, or pull requests, and you can ask anything if you didn't fully understand, or if you find any bugs or any improvements. I'm fully aware that this program or this application has much room to improve. There are some functionalities missing actually, such as pawn promotion. So for example, when you manage to take your pawn from here to the last row, it should be promoted to, for example, a queen. So these kinds of mechanisms are missing currently, and unfortunately I'm not going to be able to further this series and go on continue making videos, but we can together maybe add these features. So that being said, let's dive into our today's topic. So here we have a very simple decide move method. We only initialize, or we only call our maximizer once and return its best move. So in the iterative deepening approach, we actually iterate a for loop. So for example, let's call this variable d, and the d will start from 0, and it will get incremented in each iteration, and this d will increase the search depth by 1 in each iteration. So let's change this value to initial depth. Alright, and let's go ahead and create a new field called current depth. So this current depth will be updated by adding this d value to the initial depth plus d. So this is our current depth in each iteration. So instead of calling this maximizer with the initial depth all the time, we will now call this. So let me move that here. We're going to call this with the current depth parameter, so that in each iteration our maximizer will search a larger tree. So of course it's going to take more time, and that's why we are going to have to define a timeout in our application. So for example, let me create a new static final field, so private static final int time out milliseconds. So let's say let's make this 3 seconds for now. And what we are going to do is we are going to continuously or frequently check the timeout, and if the timeout has occurred, we are immediately break our recursion here inside the maximizer and minimizer, and immediately return from the function, and also break out of this loop and return our best move. So in order to do that, we actually have to store our start time. So let's assign the start time like this. So system current time milliseconds. So actually this start should be global because this should be visible from our minimizer and maximizer. So private start. So private int, or was it long? So it was long, I guess, because this returns long. And also we need a flag called private boolean timeout, and this flag will initially be false. It will turn to true whenever we no longer have any extra time. So this will be set inside where we are checking this timeout milliseconds and comparing with the start. So let me go ahead and do that first. So we can actually put it in the beginning of our maximizer, in the beginning of our minimizer, or both, but since they frequently call each other, it doesn't matter where we put it. So I'm just going to put this condition check in the beginning of the maximizer, and what we are going to check is we are going to check if this current time, so system current time milliseconds minus start, is larger than timeout milliseconds. So if this is true, that means that we have no time left for further computation. So we have to set this timeout, so timeout to true, and also return immediately, and let's return the current alpha that we have. And by doing this, we are actually breaking out of this loop, because what we are going to do next is we are going to add a new condition here. So if timeout, we are going to return best move. So what we did is to move this line to here. So we no longer need this one. And if you look at the condition of our decide move here, to recap, we are initializing our timeout to false and start time to the current time. So in the beginning of the decide move, we are recording the starting time, and inside a for loop we are incrementing the d value here one by one, and we are searching the tree for the increased amount of levels of the tree, and if a timeout has occurred in our maximizer, we are checking that. So this immediately terminates because we are returning if the timeout has occurred. So it doesn't call a minimizer if the timeout has happened, and it immediately terminates. And also we are breaking out of this for loop as well. So there we need to also change this condition because it's still checking if the depth is equal to the initial depth in order to assign the best move, but it has to actually compare it with the current depth, because it will start with 5 but it will become 6, 7, 8 and so on. So we have to change this with current depth. So this is almost complete, but there's a detail here. Actually we are returning the best move, but look at what happens now. So for example, let's say you have completely searched a tree with depth 5. So you came up with a best move and you have extra time left and you decided to search a tree with depth 6. So you get the legal moves and you begin with the first legal move and you update the alpha value because it was negative infinity when it was initialized, and you update the rating and quickly assign a new best move. But this current state of the algorithm assumes that your new best move in the beginning of searching the new tree is better than the previous best move that was found by searching the previous tree completely. So there's a good chance that searching the smaller tree completely will result in a better move than selecting the first best move in the larger tree. So I hope I'm explaining this well. So it's an important issue. So in order to avoid making this mistake, actually we need to create a new chess move field here called, so let's call this global best move, and we should assign, or we should update our global best move only if we can know for sure that our search has completed for a given depth. So we can make sure this is the case by assigning the global best move here. So if we assign it here, we are making sure that even if the maximizer changed our best move, it won't affect the global best move if the timeout has occurred, because if the timeout has occurred, it will immediately return, of course, the global best move before this line can execute. So it will return the safer best move instead of the newly assigned best move. So I hope this makes sense because it's a very critical aspect of the algorithm. And also we need to add a new if statement because, as you see, it assigns the best move to global best move in each iteration, including d equals 0. So whenever d is equal to 0, you actually don't have a best move. So this didn't execute yet. So we can only assign this if d is greater than 0. And if I'm not missing anything, this should be it. Alright, so we can now try out our new implementation. So let's see. Actually, we can't see if the iterative deepening works or not because it only displays the ratings at the moment. So let's go ahead and actually print something useful. And while we're at it, so let's remove the useless message that we added for debugging from this class. And instead, save that, and instead let's add a print statement here. So completed search with depth, current depth, and period, and best move so far is equal to global best move. So by looking at this message, we can figure out two things. First, we can see how many iterations we could squeeze into our timeout. So in 3 seconds in our case. And secondly, we can see which moves our algorithm has considered in depth 5, in depth 6, and in depth 7, and so on. So we should see that the global best move changes as the current depth increases. So, but we need to change something because we can't see the global best move. So let me show you. We are just going to see the ID of this object because, so here, because we didn't implement the toString method yet. But now we are at least seeing that our algorithm has completed searching the tree 3 times for depth 5, 6, and 7. So let's quickly implement the toString method of the chessMove class. So here, override public string to string return. So first of all, let's print the initial, let's print the moving piece. So we have the toString method of the piece class, so it can show us which piece we're moving. And then let's print the initial square, and also finally print the target square. So this line will summarize the chess move that is considered. So save and launch again. So as you see, oops, it doesn't show any target square. Okay, I meant target square, not target piece. So as you see, in the first 2 iterations, depths 5 and 6, it considered the same move as the best move. So it was b7 to b6. So here, this pawn from here to here. But in the 7th or the 3rd iteration, the depth 7, he decided that actually this move was better. So let me go ahead and increase this timeout a little bit more so that the algorithm actually makes smarter moves. So he can't search the tree any deeper because of the time limit, it seems. But let's play along a while. So it would be a good idea to add a blank line here so that we can distinguish the turns. So let me relaunch that. again it changes his mind in the third iteration, and this is his next turn, and he changed his mind to twice this time. So he was considering b8 to a6. So what is b8 here to a6 here, and then he considered in the second iteration e7 to e6. So it is this one, and finally he decided a7 to a6 was the better option. And what can we do here? Right, as you see, the iterative deepening allows our algorithm to improve his decision according to the increasing depth of the tree, and he can improve his decision as long as he has additional time. So if you change this timeout to, for example, a very large number, such as a minute, for example, so we don't have time to demonstrate that because this video has already got so long, but you can play with this. Then he can actually search for the tree for depth 8, maybe 9. I didn't try it, but so that's it. As I said, feel free to tell me what you think. So I hope you enjoyed watching the series, and hopefully you might I hope you learned a thing or two. If you have any ideas, suggestions, questions, shoot, and feel free to contribute to the GitHub repository. So thank you for watching, and see you around.